First of all, I thank you very much for the invitation, because for me it's a great opportunity to talk to the people who really do with the real stuff, with photovoltaic devices and things like that. And I am which one? Okay. I am a theoretician, and even most of my life I was considered myself as a mathematical physicist. So when I start to try to apply the abstract stuff to the real world, I notice that I do not understand anything what is written in the textbooks. And my strong belief was that most of the things are wrong or useless, simply to explain the basic principle of which are behind things like thermoelectric generators, solar cells, fuel cells. And after some time, we even realized that batteries, normal batteries which you have in your cars, you never find any explanation how do they work really. What is the mechanism of generating of electromotive force in them. So there is a series of papers I would like to stress that I have collaborators, which are two of them. David Gelbwasser is a theoretical physicist. Alejandro Jenkins is also a theoretical physicist who changed from high energy physics to more down-to-earth problem recently. And we even were able to convince experimental physicist Elisabeth von Hau from the Fraunhofer Institute in Dresden. She joined us also in this war against the common belief how these devices work, especially in photovoltaics. Okay, so this is my main message, that the existing textbook explanation of all this type of devices, because they are essentially are the same from the point of view of general physics, of thermodynamics or electrodynamics. So I mean photovoltaic, electrochemical, thermoelectric. This explanation are even not wrong. They are simply senseless. When you see a standard picture in the textbook in Wikipedia, for example, of the photovoltaic device, you have, first of all, famous band bending. Then you have the mechanism, which is essentially, you can call this electron or hole sliding on band bands. So one tries to explain the current flowing in the closed circuit by the gradient of some potential, or the gradient of some energy landscape. It doesn't make sense. It's absolutely against, the basic mathematical formula which shows that the integral of the gradient over the closed cycle is always zero. So you cannot produce work in such terms. And what is even more amazing, there is only one textbook where this kind of explanation is criticized. It's a quite well-known book, I think, among experts. Professor Wirfel, I think there is now third edition of this book. And at a certain moment, he discussed the standard picture with sliding of electrons, and it's quite strong, present quite strong opinion that must be something wrong with our fundamental education, that we can believe that the static description can explain driving of the current in the closed circuit. So, but this is the only place, and unfortunately he replaced this standard picture by something different, which is even less clear and involves some chemical potential and some membranes at the end of the device, which allow the charges to go in only one direction, things which looks very much like a Maxwell demon in statistical mechanics. Okay, another problem with this is, of course, the concept of band bending. this concept cannot be correct because it's absolutely in conflict with quantum mechanics. What are the energy bands? There are simple.
Excuse me. We haven't arranged that. This is the first confirmation that perhaps I was.
Yes, it was amazing. You know, we were sitting with Alejandro Jenkins in our office, and I showed him your mail from you about this about this prize, and we were discussing about this band bending for at least the last 2 years. That such a nonsense exists in the serious literature. So, of course, what are energy bands? There are energies of eigenenergies of certain Hamiltonian. This is a very well defined object. It's a Hamiltonian in the single particle representation. So one has such a simplified picture, which is quite correct because electrons are fermions, and the temperatures, the normal temperatures, are much below the how it is called, this temperature, not critical, but the temperature which in which fermion statistic becomes important. So then we can use the picture that each electron moves in the potential which is created by all other electrons and ions in the lattice. And then we can construct such self-consistent potential and self-consistent Hamiltonian, which also describes the kinetic energy of the electron, and try to solve the Schrödinger equation, time-independent Schrödinger equation, to find wave functions and energies. And these energies cannot depend on the positions. Wave functions can depend on the position and depend, but not the energies. It's like in atom. In a hydrogen atom, the energy of excited state doesn't depend on the position of electron in the atom. It simply makes no sense, and it's really amazing that things like that still exist in the literature and in textbooks and in serious paper. What can depend on the position? Of course, wave functions can depend on the position, and therefore also density of electrons. Local electron density can depend, and can be even at equilibrium easy computed using the population of levels given by Fermi-Dirac statistics and the probability of finding electron in this point. One can also introduce a local chemical potential because you can rewrite this density of electrons somehow replacing the wave function by something which depends on x and can be called a local chemical potential. Of course, one can define electrostatic potential. When we know the charges, we can compute electrostatic potential. And finally, we can define a local electrochemical potential, which is the object which really drives the motion of electron fluid. Again, one should remember there's another picture which is not so physically correct. Namely, one often, especially in semiconductors, consider electrons as kind of Brownian particles which, diffuse. A much better picture is a fluid, like water in our pipes. So it means that it has some compressibility. And then chemical potential is a pressure. And therefore, the gradient of chemical potential is a force acting not on a single electron, but on the small volume of electronic fluid. And this, together with electrostatic force, produce the effective force acting on the small volume of this electron fluid. So this is why electrochemical potential, its gradient, is really a driving force for the small volume of electrons. Okay, so what happens when we put now together two materials, like, for example, p-type semiconductor and n-type semiconductor? Assume that the chemical potential on the left is higher than the chemical potential on the right. Then this pressure, higher pressure, moves electrons to the right part of the sample and leaves some positive charges of ions, producing electrostatic double layer. And this electrostatic double layer appears in all this system, in photovoltaic cells, in thermoelectrical cells, in batteries, and this is the main object which should be studied to describe the generation of electromotive force. So this is the spontaneous creation of electrostatic double layer, and one can represent those three potentials. So one is a chemical potential, which should reach its initial values in the bulk. There is electrostatic potential with the jump generated because of this existence of this electrostatic double layer. And there is the sum of this potential, which must be completely flat because we are at equilibrium. So there is no motion of current in such a sample. So this is the equilibrium potential at the p-n junction. Okay, so how one can generate in such system electromotive force, for example, by illumination. So this is something what we, in fact, quite recently understand in detail. So what is the main mechanism? You cannot do it by any static means. Unfortunately, also, you cannot explain this by Landauer equation. You need something more. You need dynamics. You need motion in this double layer, which pumps electrons from right side to the left side, reducing this electrostatic double layer. When this is reduced by pumping, by active pumping, then the jump in electrostatic potential decreases, and you get a non-trivial electrochemical potential. And this final effect of non-trivial, non-flat electrochemical potential, this is the driving force, because, you know, electrons are moved by pumping mechanism, and then here you obtain higher chemical potential than here, so the electrons can go around. And this is the only way to generate current in the closed circuit. You must pump something against the gradient of potential. And this pumping must be dynamical, it must be a real mechanical pump, which is here created by a mechanical object, namely such a double layer oscillates, because it's, of course, it's a state of some minimum energy. So when you disturb this, it oscillates. And this acts like a normal hydrodynamical pump. The one consequence of this picture is that the open circuit voltage should not be larger, and very often is close to the difference of this initial chemical potential, which were introduced into the model. Okay, so now some summary of this picture, which is essentially a picture of electric generator. So we have engine, which has its own piston, but the same piston acts as a pump. The energy, of course, I didn't say it before, is provided by light, or in the other devices, it can be provided by chemical reaction or by heat. In the case of photovoltaic devices, is exactly provided by light. And I will show a little bit also equation which could explain this, the simple model. So we have the following main ingredients of this description. First, the electrostatic double layer is formed at the junction of two materials. So it could be p-n junction, it could be electrolyte, electrode interface, it could be metal for some types of thermoelectric generators. But this junction is necessary to produce this double layer. Double layer can oscillate with a given frequency. Sometimes there is more complicated situation like in organic photovoltaic devices, when you can have few, 2 or 3 frequencies of oscillation of such a double layer. These oscillations normally are damped, but if you supply energy from external non-equilibrium bus, it could be light, it could be heat, it could be chemical energy, and then you need a special mechanism which involves feedback. So this is typical for all engines. All engines are based on kind of self-oscillations or self-rotation which are related to feedback. So this oscillating part somehow also is steering the income of energy. So I will explain this, say, more mathematical model soon. So then we have the energy drives self-oscillation. And the same piston acts also as a pump on electron fluid. So this is a very economical solution provided by nature, that you have the same, say, mechanical object, this piston, which extracts energy in a form of mechanical work from the environment, but at the same time pumps electron fluid. Okay, let's came back, I think. Okay, so now there is something, it's maybe funny, but I like this because it was the first real model of a heat engine which I understood from the point of view of dynamics. So I learned this from Alejandro Jenkins, who wrote a review paper on self-oscillation and described all different types of engines, including this. This is called, this is based on the engine used in a toy, put boat. You cannot buy it in Europe probably because it's too dangerous for children, but in India it's very easy to buy this. I have even one at home. So this is exactly the hydrodynamic analog of, for example, solar cell or thermoelectric generator. We have a container with water, and at the top there is air mixed with steam, and you have a flame which heats water. Then after a while you will hear this noise, put. It means that the surface starts to oscillate. And these oscillations are used in the case of this boat to propel this boat. But here one can combine this with a pump, water pump, when you have some valves to make it more effective. This engine can suck water from the lower reservoir and then put it into the upper reservoir, producing work. And exactly this is the basic mechanism is the same as in those devices I considered. We have an interface, we have a surface which can oscillate, and this oscillating surface is a piston which is used to extract energy from environment, and at the same time is used to pump the fluid in the circle, which can be closed, and this is exactly what we need. One can describe it in the using simple equation of motion. So one equation is a kind of Newton equation for this degree of freedom. We have some frequency, there is some natural frequency of this configuration. And there is also some damping, which is some internal damping, but also it's a damping created by the flow in this system. And on the other side, you have its quantity of the steam here, which varies because of heating. So there is certain equilibrium quantity, so what is important is the difference of this quantity of steam from some stationary value. So this is the one equation, and the other equation is quite universal. This pair of equations appeared in many of our papers. The other equation is a kind of balance equation or, for this quantity of steam. So it's created with constant rate by the flame, by heating, but also this steam can condensate on the cold surface of this tank. And this depends on X. And here we have exactly this feedback between this source of energy and this mechanical degree of freedom which has to oscillate it. Under certain simple condition on this rate of condensation, you will get oscillation. So that's nice exercise on dynamical system. So here it is repeated, but in other language. It's repeated in the language which can be used, for example, for photovoltaics. So now this X is this kind of position of width of this double layer, which can oscillate it. And N is a number of excitons, say generally. So the number of electron and hole pairs. And again, it can be controlled by this X because when this distance between these plates increases, there is less probable that this exciton recombine. So this is why you have a feedback between the process of recombination of excitons and the geometry of this double layer. So again, when certain condition is satisfied, such system describes self-oscillation, and this engine and pump starts to work. Okay, so now about implementations in photovoltaic. I'm not going into thermoelectric and batteries at the moment in this talk. So, first of all, the oldest, oh no, maybe not the oldest, the most known semiconductor photovoltaic. So here it is known that at the p-n junction there are plasma oscillation of this layer with terahertz frequencies. I will give later some references to the paper. It was observed and there's no doubt. In organic photovoltaic is even more interesting because this electrons and holes are not really free. There are still, they form excitons, and there are some vibronic modes at the interface between donor and acceptor materials. And exactly these modes vibrate, and they are responsible for the action of this piston. They can also accelerate charges and can also extract energy. The less understood, I would say, it's the oldest, the first photovoltaic cell, which is based on electrolyte interface. Here we didn't find any really direct experiments showing what is going on this interface, what type of oscillation one can observe. There are some indirect results, but not really direct. It seems that it is most complicated situation. So now few words about existing experimental evidence. In the case of p-n junction, it was already observed in the end of 90s that there are terahertz plasma oscillations. They were excited by strong pulses. laser pulses. But later, say in 2012, a group from Japan observed this terahertz plasma oscillation in actual PV cells. It's not so easy to measure terahertz radiation, so this is why the progress is not so fast. There are much more interesting experiments in the case of organic photovoltaic devices, because they have more tools to observe the dynamics of charges. They can really see the traces of the charges, how they move in the samples, because the complicated structure of these materials gives some more insight. The moving charges modify energy levels, and it can be observed by optical methods. And they really observed oscillatory components in charge separations. So charge separation is something what we would call pumping. So the process when the charges are removed from far from the junction, and then observed that exactly this charge motion possesses an oscillating component which agrees in frequency with some modes of this optical phonons, I would say, at the surface. So they have even more interesting, I would say, observation in this kind of system, namely, they illuminate this with infrared radiation, so much lower frequency than the optical radiation which drives this photovoltaic. And exactly when this radiation was in resonance with these modes which oscillated, they observed increase in photocurrent. So they simply somehow were able to get to this piston and externally, amplify its motion. So for us, these experiments are absolutely sufficient to justify our approach. But of course, nobody here was even thinking about connecting this to the basic principle of operation of photovoltaics. For all of these authors, there were some kind of side effects, yes, which, okay, could be interesting, but not really fundamental. So I think one really needs to work more on and give more information about these processes. Okay, so now some concluding remarks, which follows from our work in the last almost, I would say almost 10 years. So first of all, that generation of electromotive force cannot be described in terms of some gradients of stationary potential. Also, Onsager relation, which was essentially discovered because Onsager wanted to describe a thermoelectric effect, also cannot describe thermoelectric effect. They can describe some, thermalization or some passive flow from one material to another, but cannot describe generation of electromotive force. One needs some time-dependent, non-conservative forces to generate work. And this follows essentially why I started to work on this subject, because I noticed in the literature that there is no mention even about time-dependent forces in all these devices. And from the general consideration of, which is now called quantum thermodynamics, it followed that there must be always something like a piston which oscillates in time, or rotor which rotates. It must be some kind of periodic motion in the system. You cannot do it in time-dependent way. So the system producing electromotive force should be treated as pumps propelled by heat, chemical engine, where the energy is of course supplied from the non-equilibrium environment. Again, I already said it that this is a very economical design because the same piston acts as an engine piston which extracts work from environment, but also is a piston of a pump which drives the electron fluid and drives the circulation. And then when we started to think about these problems, we discovered many other fields. So we have no manpower to work on this, but there are the same problems and the same solution can be proposed for biological systems, which are also engines, so, and also pumps, you know, and what we have in our cells, there are essential engines and driving pumps. Also, chemical catalysis seems to belong to this, this field. So there are some kind of engines and work is used to put molecules together and not by static change of the potential landscape like it is usually described in textbook. But anyway, this is something for the future. This talk I wanted to stress to application of this to photovoltaic cells, and thank you very much for your attention.
Can we ask a question?
Yes, of course.
To this frequency, is it if our PN junction is in thermal equilibrium
Yes.
with the rest of the world, does this oscillation there work, or it just is activated when we shine a light or drive it out of equilibrium?
It's activated when we shine light. Of course, there are always some Brownian motion, yes, but this is such small amplitude that it cannot do anything, yes, because at non-zero temperature, anything can have some motion, but it's exactly driven by external field. So there must be difference of temperatures to drive it. So.
Thank you very much.
Yes.
Is it related to the light wavelength, which is related to frequency, and should it be observed any wavelengths that for those wavelengths the
resonance?
Resonance.
No, resonance is on completely different frequencies. Do you think about light which is used as a source of the energy? This is the same limits as for standard theory that the energy should be higher than the band gap. But you can activate additionally these frequencies, but they are in terahertz region for solid state, or it's low infrared. It's 1 order of magnitude higher than terahertz, I think. In the case of organic photovoltaic. And this can be activated by the external infrared radiation. This is one of these experiments. This activation was observed essentially there's only a single paper about this. Okay, there's this is increase of photocurrent stimulated by resonant IR frequency. So this is not the frequency of the light which drives the solar cell, but this is frequency of this optical phonons on the surface, which serves as a pump. And
is there any spectrum shown that as a function of wavelength for a given frequency there is a maximum or
yes, it's resonant. It's exactly resonant. They reproduce exactly the structure of this frequency of the surface phonons. So this is, for me, it's absolutely striking, you know, proof that we are right with this picture. But, you know, to convince people is the problem.
Thank you again, Professor Alicki.